Won't you take me to that place when I lose my sense of time, where I escape my fate, when I feel the most alive? Won't you play my favorite song, my favorite song, play my favorite song? Won't you play my favorite song, my favorite song, play my favorite song? Cartoons in the night, I don't wanna wait, I don't wanna wait, yeah, so yeah, zing. I wanna feel it in my body, I feel it in my body, yeah, feel it in my veins. Wallah, I feel it in my body, I feel it in my body, yeah, zol, yeah, zing. And play my favorite song, my favorite song, play my favorite song. Won't you play my favorite song, my favorite song, play my favorite song? Oh, when I see you want it to come on. Oh, when you want it to come on. You want it to come on.
All right. Hi, everybody. So I was walking over and I was like, oh, wow, that's a large Cal Day event at Memorial Glade. And I was like, oh, I see. And then I realized, anyway. Okay, so we have any visitors here today? No visitors? Hi, visitors. How you guys doing? Are you guys like high school kids? Is it weird that there's like a huge number of people smoking weed out there or what? Anyway, I don't know. What's that? Yeah, you're local, so hey. Are you guys any out-of-state visitors? Where are you visiting from? Boston? Kentucky? Cool. Kentucky, nice, welcome. I grew up in Texas, which isn't really Kentucky-ish at all, but it gets really hot in the summer, at least there. This is a normal, if you're visiting from out of state, this is the normal weather from now until like October. So it's a cool thing. All right, anyway. So today we're going to be talking about our final new data structure of the entire course. Next week we're going to have 2 cool applications, and then we'll have a goodbye lecture. Isn't that weird? How'd that happen? Anyway. So tries is the topic of the day, and we're going to start by summarizing what we've seen before so far in the last so many weeks. So we had a bunch of different ways to implement all kinds of different data structures, and I'm just going to focus on the ones which involve searching by key identity. So we had sets and maps. Those are our abstract data types where we want to retrieve things based on their identity. So we had 2 different flavors. We had this tree-based approach. We had a bad tree, which is our binary search tree, and then we had some faster versions. And then we had 2 different versions of hash tables, one of which we talked about in class, one of which we did not, but which I included as an optional, which maybe you'll run into in the world. So those are two different ways of doing search by identity. Okay. Now, more recently, we've been talking not about data structures, but sorting. And the first type of sorting we spent a lot of time on was comparison-based sorts. We spent 3 lectures on this. We talked about selection sort, where if you heapify first, then it's actually heap sort. We talked about merge sort. We talked about partition sort, which is called quick sort. And then we had insertion sort. Now, insertion sort, there was actually a connection between insertion sort and quick sort, which is that if you just insert into a BST, you end up getting quick sort. So there's these interesting connections between selection and heap sort and insertion and quick sort that we saw. Oh, I'm going to turn on that tamper monkey thing. It's gone. Death to that thing. Okay, but I've installed it now, so thank you again for creating that script, student friend. All right. Oh, yeah. We'll applaud this. What are we applauding? The fact that this is not showing up anymore. Years of struggle with this thing is over. Hooray. All right. So that was our comparison-based sorting algorithms. And then in the previous lecture, our guest lecturer, Chris, talked to us about 2 different types of sortings that did not involve sorting by comparison. One of them was counting-based sorts, where you count the hearts and the spades and the diamonds and the clubs, all that stuff, and we get a counting-based sort. But this only works if we have a small alphabet. We generalize these by talking about these digit-by-digit sorting algorithms. So we had both LSD and MSD sort, and those require you to sort by digit, and the way we did it in lecture, kind of implicitly, we didn't go through a full example, was by counting as for each digit. And there's other variants of these sorts. You don't have to actually do counting sort by digit. You could actually sort each digit by insertion or selection or partition sorts, but hey. So those are our 3 different types of sorts. And the reason that digit-by-digit sorting was better than counting sort was this lets us sort, say, long numbers by considering each digit at a time. Now, what I'm going to do here is show a connection, not between the comparison-based sorting algorithms to each other, but a connection between these search data structures and these sorting algorithms. So first, I'm going to note that these search by key identity data structures, these are very similar to these comparison-based algorithms. They use compare-tos to resolve the ordering of these objects. Ultimately, we form an ordered data structure, and that lets us retrieve by key identity. And these are roughly like our hash code or equals. The maps here that use hash code and equals, that's roughly analogous to this integer sorting algorithm or these counting-based sorts. In these cases, you are cheating by abusing space in a funny way, and you are getting something that lets you get very fast, better than logarithmic search times by cheating and exploiting space. And that's what the counting-based sorts do. The next question then is, what would be the equivalent of a digit-by-digit sorting algorithm? So if we're doing analogies here, just as a search tree is to a comparison-based sort, what a hash table is to an counting sort, what would be the equivalent searching by key identity? It seems like there's a hole in the space of possible ideas we might have. Now, if you're somebody who smoked a lot of weed before coming, this is probably like, dude. So, but anyway. All right. Hopefully you didn't, because I don't think that you can come to a CS lecture having smoked a bunch of weed and have a good time. Maybe. I don't know. Anyway. There's water up here if you need it. All right. So, anyway. So what would it mean to search by digits? Well, it would need to be something analogous to digit-by-digit radix sorting. And so I'm just going to propose this data structure, which we'll call a trie, and I'm going to kind of spoil it here and give you a sense of what it might look like, and you guys are going to try and invent the rest. So let's suppose we want to build a set in this case, and that set contains the words SAM, SAD, SAP, SAME, A, and ALLs. And what I've done here is I've started constructing this data structure that contains all of these items. It is not a search tree. It's something else, and what you'll notice that's special about it is that it's digit by digit, and somehow this S and this A are shared by SAD and SAM. So what I'd like you to do is just use your intuition to try and build the rest of this data structure, and then we'll probe its properties. So I'll give you guys 45 seconds to a minute to ponder. Okay. 5 more seconds. All right. So let's suppose, and we'll be doing this text over here will make sense in a minute after we finish filling things in. So let's suppose we then put in sap. Okay, what do we do? What do we need to add to our tree? A P. Okay, good. All right, here's the letter P, and let's connect it up. All right, then same shows up. Okay, so here's sap, and then same, we got to add an E, and it's going to go below S-A-M-E. And then, what about A? Okay, so someone tries to put A in. What happens? Well, we need to put an A, and we can put it up here. That seems reasonable. And if we have alls, then we need a WLS. So I'll take these, and I'll copy them. And there we have it. And I have to give them some new letters, but this is the data structure we end up with. And hopefully I didn't mess anything up. Any bugs? S should be, thank you. You guys have discerning vision. Let's make the letters larger even, if it will let me. No, okay. It's not worth it. Okay, you guys, most of you hopefully can see what the letters are. I'll zoom in for a minute. All right. All right. So one issue, and there's a hint here about how to resolve this, is if we call contains on this. Because remember our set has 2 operations. We have insert and contains. Right now, while all of this text is here, we have no way to differentiate. So does this set, if we look at this list, should it contain SA? No, we haven't inserted that. Now there's no way to tell that SA is a word, not a word, and SAM is a word. So what could we do, maybe? Yeah. Mark the ones that are the end of a word. So in that case, it could be, actually what we should have done is when we got to SAM, or the M, the E, the P, the D, the A, and the S. These all should have been colored in, and I picked blue. So in that way, you're marking the ends of words, and they could be, one word could be a prefix of another word, so SAM and SAME. So in this case, when we call contains, we just walk down the tree, and we say, for example, let's full screen this again so we can get some more pixels. So we got S, A, M, it's blue, okay, so we should return true. S, A, it's false, right, because it's white. We get to A, blue, true, and does it contain nothing? Well, I'm going to say no, we have not inserted the empty string. Okay. So in this case, I would say we have a search miss. Let's do another one. Contains, I don't know, S-A-Q. All right, same deal. So in that case, if we do S-A-Q, we go S-A, and then, there's no Q. So we fall off the tree. All right. Any questions about this idea? Okay. So there's also an animated demo if you want to see a longer example, but I'll just leave that there for your benefit later. Okay, so this is a new third, and there's many more, by the way. There's just bajillions of different search data structure or storage data structures out there, but this will be our last one for our course. So we have our binary search tree, old friend. We have our hash set version of a set, and then or you could just call this a hash table if you'd like, and then we have our try. Okay, so it's a third philosophy. And this is just what each one looks like, and they're fully redundant in many ways. I mean, there are some differences, like this one keeps track of order in some nice way, and this one has very fast search. And so we'll explore what are the nice properties of the try that made it worth doing an entire lecture on. You get some sense that there are some benefits, like, I don't know, what's something here you notice that seems somehow beneficial? What do you think? Yeah. Yeah, so it seems like if you're looking for something where you fall off the tree quickly, your search might get resolved more quickly. Other thoughts? Yeah. Yeah, you could potentially use less space because there's some reuse. Now, there's actually even more compact data structures. There's one called, and this is the real name, I'll just put it up here for fun. It is the dog. All right, dog. Okay, I'll just mention that exists, which is a directed acyclic word graph. So if you're like, how do you make this even more efficient? There exists a thing. We won't talk about it. All right. So what is the thing we actually built? Not a dog, but a try. And it's short for retrieval tree. Now what's funny about it is the original inventor, Edward Fredkin, he called this a tree, which was a bad idea because we already had tree in computer science. And so it was changed to be try instead. So why if you look on Wikipedia, you see that Shinobu back in 2008, you can go look this up and you can say, Why did Edward Fredkin choose that word? Just for everybody who's reading. Since he pronounced it homophonous to tree, didn't he realize that it was a pretty stupid choice because that would make it impossible to distinguish the words in speech? If he was so desperate to combine tree and retrieve, surely he could have done better. All right, Shinobu was just cruel. Is Shinobu still active on Wikipedia? Let's see what else he's up to. I haven't ever tried this. That's a different Shinobu. Hold on. Oh, no. This is getting... Yeah. It's fine, actually. It's just some kind of ninja thing. All right. I don't know about these things. Sorry. I'm 36 and don't know about whatever's happening in anime life. Okay. Let's go check it out. Let's go to talk. Is Shinobu still here? Yeah, there he is. Shinobu. Okay. Yeah. How do you know if he's still... Where do you see, like, their edits? Left? Oh, the user is left. Oh, sad. Okay. Oh, well. Gerbrant. Changed their name. Okay, anyway, moving on. Now what I'd like you guys to do is try and think, it's a little more rigorously. Let's try and use our asymptotic skills. Give me in big O, big theta, whatever you feel like you can give the best answer. For a try with n keys, and let's say a key with L digits. And when I say key, I mean I'm inserting a key, or I'm checking it contains. That's the key. So, for example, if I tried to insert potato, L would be 6. And in this case, the try in this case has n keys. 1, 2, 3, 4, 5, 6. Okay, that's what I mean by n. What I'd like you to do is give me what is the worst case insert runtime, search runtime, and the best case search runtime for n keys, L digits. And actually, I'm going to put some numbers here. N equals 6 for this case. All right. Okay. Almost done. All right. I'm going to spoil it. I don't know what answers you came up with, but here are mine. So the worst case insert is L. So no matter what you insert, it just takes you L time. It doesn't matter how many keys are in the thing already. You're done. Worst case search, also L. So it doesn't matter if you have 20 bajillion things in your try. You could still find if something's in there in L time, where L is the number of digits. So again, potato, 6. And the best case search runtime would be 1, which is just the first digit is a miss. Now compared to a hash table. In a hash table, the time to compute a hash code for a key that has so many digits, if it's digit by digit, assuming that the hash code actually computes all of the digits. Oh, actually, you don't even need that assumption, because you also have to check equality. Because hash table, hash code, and equality both take L time, each of these operations takes at least L time, because you have to compute the entire hash code of your key in order to check if it's there. But in the worst case, you have to go through a list of n things. All right, any questions about these runtimes? Yes?
What if there's like a million different letters, and when do you have to iterate through all?
So I said assume that the child can be found in constant time. So we haven't talked about, but yeah. So the alphabet size is irrelevant, given this assumption that children can be found in constant time. Yep. Are tries typically only used with words? I mean, they're actually used in a number of contexts, and we'll see that they're used, for example, in compression algorithms. So you can do it on an alphabet even of just size 2, and it can still be useful. Yeah. And if you're doing words, you'll often use something like a directed acyclic word graph. Yeah. A key is, an entire word. So an example of a key would be Sam or sap. Yes. Yeah, so L is the size of the keys. Yeah, so good point. The runtime should depend on the size of the keys, and yes, that's L. Yeah. Yeah, if you had 100 keys with 1,000 digits each, yeah, if the thing you're looking for has 1,000 digits, then yeah, you have to spend the time to look at all the 1,000 digits in the worst case. But that's true of any search structure, unless you have like a cached hash code. Yeah, all right. Okay, so to summarize our performance, if we look at this is a kind of ugly table. So hash tables, of course, their performance is kind of on average, and you have to have this star, and I didn't tell you what the star means, but the star indicates that things are spread out nicely. On average, a hash table will take about L time to do a contains operation. A binary search tree will take between L log n and L time. Best case means you find it in the root. Worst case is you're at a leaf. Tries, they are L in the worst case and 1 in the best case, and you can digest this table later. The more important point is that, like a binary search tree, the comparison that you do is done digit by digit, and that's actually true for a hash table as well, which allows us to occasionally, if we're lucky, skip some characters. Okay? So in other words, as soon as you see a mismatch, you know that you're done, and that happens in a binary search tree as well. Now, hash tables, I do mention here that unless you're doing some kind of caching, hash tables have to maybe look at many unnecessary characters. So if I want to know, does some 1,000-digit long thing exist in my hash table, I have to compute the hash code for that huge object, and that's going to cost you some time, unless it's already been cached at some point. And like hash tables, what's nice about it is it doesn't matter how many keys you have, the searching time is going to be constant, but unlike hash tables, which have this star, which is like, well, on average it'll be irrespective of the number of keys, this one always works. Okay, so there's a lot to digest here, and we could spend a half hour just talking about this, and if we were doing like a 61B job interview thing, then it would be fun to, spar about it. But I'll just leave this table here, and what I'd like you guys to do ideally is argue with each other about elements of this table, and maybe reconstruct it, like if you're laying in bed trying to think of something to do, you can try and come up with this table if you can't sleep. All right. Which I think I did last night, by the way. I was like, I got to get ready for Tries lecture, so I'm going to think about this table. So I fell asleep dreaming about this table. It was nice. All right. So, what good are these tries? I mean, I understand that they're a different approach, and they seem to have this nice runtime behavior. And that's true. It is nice that they have this nice runtime behavior, but we'll see there's some issues. But actually, the main reason that tries are significant and why anybody cares about them is not this table. It's not something about, hey, this is the way things are done. Because if you think about it, what is the method that Java requires of all objects in order to allow efficient retrieval of objects? Hash code. That indicates that hash code in the real world is what people care about. It's not something like, for a try, what would you need? What kind of method? It's a hard question. So imagine that there was something called a try map in Java. That was something that computer scientists had settled on. What would be the special method that each object would need in order to work with a try? What? Yeah? Yeah, pulling apart its components, getting a digit. So in a world where try maps were important, there would be a get digit method. There is not. And seems at first glance a little strange because, oh, well, look, you get this better runtime. But on a practical basis, a hash table is just better. It's more practically useful, and there's a lot to think about there. So what good is a try if it's not, this amazing replacement for hash tables? Well, it's that it does two things that neither binary search trees nor hash tables do well. So first operation that tries are really good at is something called keys with prefix, I'm calling it. So what this does is it returns all keys that match a given prefix. So if I ask for all the things that match SA, I get SAD, SAME, SAM, and SAP. And that could be more efficient than if it's spread out over a hash table. Imagine trying to find everything that matches SA in a hash table. You can't do it in any efficient way. You just have to look in every single bucket. That's slow. In a binary search tree, you could do a little better, but it's still not as nice as in a try. And then another operation is longest prefix of. So this is a very common operation that you use in, for example, routers that are trying to route around packets. If you ever take networking, you'll talk about why longest prefix of is important. But in this case, let's imagine I'm trying to find longest prefix of sample. Well, in this case, it would be SAM. That's the longest thing in the entire data structure that is a prefix of sample. And actually, next week, we'll see an example that involves data compression. Okay. So those are two operations that are good, and that's why tries matter, that they do these two things well. Yes, they're a little faster, but there's a lot of little caveats. What's really important is this. Okay. So let's talk a little bit about how you might implement these before we talk any more about performance and exactly how these operations work. And let's focus on how you would actually build one of these things. So some of you, if you did the gold points, or if you're still working on the gold points for Project 3, this is the data structure we were thinking you might look ahead to see. And many of you may have gone and looked at the Princeton implementation. So let me demystify what that was all about, and how we might build this. So the most naive way to build a try, but the simplest way, is to say, okay, for each node in my data structure, let's first set a coloring, so Boolean exists. This is blue or white, but here I'm using true or false. And let's also have an array of links. Now in this case, what is that array? Well, it's going to have one link per alphabet character. And so in this case, I'm assuming my alphabet is digits between 0 and 128, which will handle letters in English. Now in this case, and this is all the node class is. So in this case, what you'll do when you start is you create a root node, and you just create it and you don't set any, it exists as false by default, and it has a whole array of links. Okay? Now what's interesting is this is the drawing we've been using to understand a try. That's the intuitive one. But this naive approach, it actually, instead of storing explicitly each letter, what you'll notice is that the node does not have a variable called letter. It does not have an S or an A in it. Where is this information stored about S? Well, it's stored in the parent's link. So really what a try looks like is you have the root, and it has a whole bunch of links, 128 in this case, though I'm only showing some smaller number, 20-ish. And so the fact that A is valid is because this link goes to a node. Where would B go to if there is nothing that starts with B? What do you think? Null. So if your link number B is null, then you know that key is not valid, or it doesn't get you, that letter is not a valid start letter for any key. All right, so this is what we think of conceptually. In this implementation, what you end up with, right? Remember our old allegory of the cave where we are the manipulators of reality. This is what the people in the cave see, the shadows flickering on the wall, and this is what we're going to do behind the scenes, just like you guys did with Project 1 long ago. Okay, any questions about this approach? Yeah. Sorry, is a try over the bits of an object, or I think it's better to say over the digits of an object. Oh, would a try over the bits of an object work? Absolutely. It just doesn't necessarily have nice interpretations for what the digits are, but that's one way you can build a try out of anything. Yeah. There's not really a drawback. I mean, I would argue that there's a reason to believe that storing the letters in the nodes can be useful. This approach is nice because it means you can instantly get to where you want to go, but we'll talk about alternate approaches in a bit. Yeah. It's incredibly wasteful, yes. So, whenever people would copy and paste this code and try and use it on Project 3 and say, why doesn't it work? We would be like, I think it might be a little wasteful. All right. So we'll get there in terms of making it better. Okay, well, I want to stick just to the simple implementation for the moment and see what it looks like to actually implement a try. Now, because we're getting to the end of the semester, I don't want to go into a lot of detail here because this is more of the same. I mean, it's clever and it's a little harder than tree insertion like you guys got to do on the earlier labs and on the midterm. So it's just a slightly different trick. So in this case, we have a put method where you try and insert a key. And we're going to use recursion in this case. We have a private helper method. And as you guys may recall, often with these private helper methods, we add a parameter that's going to make the recursion possible. So in this case, rather than what you guys saw in the binary search tree case where we would add a node argument to our helper function, here we add both a node and an integer. Okay? Now it's very clever. It's not something I expect you to just look at and think, oh, okay, surely it is so. But it turns out that it works well. So if you want to insert a key, you say, please put in the root this key starting with digit 0 of that key. And so this D, you should think about it as which digit of the key you're currently thinking about. So if the node in question is null, we create a new node. And at the very end, we'll always make sure to return X. If D is equal to the key length, we set the color to blue and return the current node. that we just created, or maybe that already existed. And if it was not the final digit, right, we're inserting something where we're only on like digit 5 of 7, well, in that case, we get which character it is. We request the digit. This is the dth digit of the key. We then set the appropriate link by doing the recursive insert. Now, again, I only if you really, really deeply understood tree insertion do you have any hope of understanding this put method as I'm explaining it right now. So if you don't fully understand it, that's totally fine. But it's a very clever and cute algorithm. Okay, so just to give you a flavor. All right. So that's how you could implement it. Once you've done that, the get method's easier than the put method. This one's actually pretty tricky. And at that point, you pretty much understand how a try could be implemented, even if you haven't digested every little bit. Okay. So let's return back to what I think is the more interesting question. While this is clever, I don't think there's anything truly new. Here I think it's maybe you can get a deeper appreciation for the data structure itself rather than implementation details. So recall I said why tries matter as they support two operations, keys with prefix and longest prefix of. What these are, and as I mentioned before, when we ask for keys with prefix sa, it's going to give me sad, sam, same, and sap. All of the keys which are children, so to speak, of sa, and then the longest key starting with sample was sam. So I'm not going to go over implementations of this just because I think it's not that interesting for a winding down the course lecture, but I do want you guys to try and design one of these. So what I'd like you to do is, given what you know about the implementation, give me an algorithm that will allow me to compute the longest prefix of a key. And however you want to try and phrase it, go for it. Try and convince your neighbor that yours works. Whatever feels right to you. Okay, we'll see if this is possible and out loud without code, but maybe it is, maybe it isn't. I don't know if this is a great question to ask, but we'll find out. All right, anybody have an algorithm you want to explain? Sure.
So, like for example, is that okay? Is that like to ask for the starting node? If it is, so you're going to ask them to see if it links to the return character.
Okay, so check each digit in turn. Okay, walking down the tree, then what? Okay, at some point you find the next isn't there. Then what? Then return all digits so far. Sorry about the bullet points. Why? There's one little issue here, though. I'm not worried about if you run out of digits. This algorithm is described as very close, but there's one tiny issue. Yeah? Yeah, you have to make sure that your last one's actually blue. So what do you need to do? So as you're walking the tree, what do you need to keep track of? I guess I would say walking down the tree, keeping track of the most recent blue thing. At some point you find the next isn't there, then return that most recent blue thing. Okay. Now this is not a full algorithm, but it captures the idea. Okay. Now the full details will end up being some code that looks a little bit like this, but we're not going to do it now. I got another one for you. T9 texting. Now this is always fun. How many of you guys ever sent a text using this type of texting? Cool. Nice. Now eventually that's not going to be true anymore, but I'm glad that we still have some people. So as you never had to write text messages like this is how it went. If you wanted to write the word good, this is the old way of texting. So what you had to do in the old days when you just had physical buttons on a phone instead of a screen, how many people still have physical buttons on their screen? Clamshell friends? I don't want to call it. Yeah. Anyway, all right. So in the old days, though, the really old school way of texting was if you wanted to type the word good, you would press 4 in order to get the G. Then you would press 6, 6, 6 for O, 6, 6, 6 for O, and then 3 for D. There you go. You have typed good, but that took you a bunch of key presses. An innovation was discovered, which was, well, if someone types 4663, they probably did not mean like HMMF. Okay? So what I'm going to do is I'm going to give them all of the words that match, and I'm going to order them in the order that they occur. And then if I don't think the word, it shows on the screen, good, home, gone, and hoof, and good's currently highlighted. You press star to switch words. And if you don't see your word, well, you press 0 and it'll list more of them. And what it could do is adapt to your tendencies, which is nice. So, question for you. How would you implement T9 texting? Hint, maybe you should use something from today's lecture. And if you have something like a try set or a try map, please give me the types, okay? Whatever those might be. You don't have to do that, I guess, but that would be weird. Okay, good luck. Okay, I'm going to spoil it with my answer. So what I had in mind, and this is, again, we don't have real data types here, so that's one of the reasons last year I found it was kind of hard to discuss this because they're all kind of made up. But what I thought is maybe you would do something like a try map from a string, in this case, to a tree set of weighted words, where weighted words are words like good that have a certain weight. So good would be a relatively high weight word, whereas uncommon words would have a lower weight. So what is the key in this case? Well, it's a sequence of numbers that I happen to store as a string. Maybe you would decide it's an integer. Doesn't really matter. But some kind of thing that could be decomposed into its digits. I picked string. So that string would be 4663. And then what the values would be is, well, the value would be all possible words that go with that. So good, home, gone, hoof, and hood. And so the tree set is just going to store all of those. And the reason I picked a tree set is I want it to be ordered in some way. And so when a word is used, we'll increase its weight and move its position in the tree set if necessary. Now, one quick note here. If we have a tree set of objects and we just change their weight, that doesn't move them around in the tree. So how many people, out of curiosity, on Project 3, changed the priority of something inside a priority queue, but didn't change where it was, and then had to debug that? Anybody? Yeah, all right. Hello, friends. Now you know about putting mutable objects inside sorted data structures. Very dangerous. All right. Now, there are lots of other things you could do. I picked a try because it was cute, because I know the digit-by-digit matching works. Here, I'm not actually exploiting those two new methods, longest prefix of, but you could, right? You could do it by doing, or all prefixes, or all words that match prefix, and then you could give words that don't match it directly. And then you could have like something more like autocorrect or whatever else. All right. So that's just one approach. I thought it was kind of cute. As an excuse to use tries, we could use this, because we're doing digit-by-digit matching, but a tree map and a hash map would have worked just as well. Okay, just a thought. Yes? Yep, so you could certainly use a priority queue. Now there's one issue, which is that my user interface is supposed to display many choices. So that's okay, maybe, but getting the top 4 things out of a priority queue is a surprisingly annoying operation, because what you have to do is delete the top 4 out and then put them back. Yeah, so it seems a little ugly. All right. Now, if you mess up on this problem, I want to warn you, okay? And I'm going to be reiterating that you guys are now being empowered to do amazingly important things. And so predictive text, not so important these days, but in 2011 there's a story about a man who was convicted of manslaughter for stabbing his friend to death after a predictive text error ballooned into an argument. Now what I find interesting about this is it happened because he sent a text message saying, "What are you on about, mutter?" Mutter being a local colloquialism for a person who behaves in an antisocial manner. However, mutter, which is like deep slang, got turned into nutter, which is like also kind of deep UK slang, which means deranged. Okay, so mutter, fine. Nutter, not okay. So then you were stabbed. Okay. Anyway. Thank you, Andy Chalk. All right. That's a good name. Yeah, Andy Chalk. All right. So tries. All right. So they give you good performance. They do character-based operations. You can use them for cute texting problems, but they're not necessary. But there's some issues. One is that the way we've implemented it takes tons of memory, and it's because we map from a node to its children using a data-indexed array, kind of like we did when we introduced hashing. We had a huge array of size R, and it uses tons of memory because every node uses R memory. So there's a bunch of different ways to fix things. One of them is using other data structures that are closely related. We'll see this one very briefly at the end of lecture. This is this other one I've alluded to. There are many others. This is a very rich problem. Unfortunately for you guys, pretty much solved in computer science, but it's a cute one. All right. I'm going to discuss a different approach, which is rather than doing something totally new, let's think about a better way to track children than just using an array. So what we saw before is that all of our children were tracked by an array of nodes. And so how can we save memory? What can we do to improve things? Like what's something we could use instead of a node array? Yeah, a map of some kind maybe. Okay. Well, I'm going to use an example of a map, which in this case will be like a tree-like structure, a binary search tree. And this is going to be just the unrolled picture of what's really truly going on. Okay. So in the approach we have so far, this is before we do the map thing. I'm going to note that we have a root node that has a huge array. This item does not exist. It's false, but it has some links. So 97 is some letter in English. That gets us to, what's 97? Is that S? Anybody know? A? I think it's A. All right, whatever. So we go to A, does not exist, and then we go here, some other thing. D. Oh yeah, here it is. All right, we figured it out. This is A. This is C, this is D. All right, we're good to go. So this very simple to see data structure in all the way down, like our environment diagram version, lots of boxes. Okay, we had to use dots. Now what we could do instead is say, okay, well, instead of tracking by an array, we could do a binary search tree instead. So here, rather than having an array of all the possible children, that some of which we don't use, we only have the ones we do use. In this case, C is arbitrarily the root, and A is its child. So this represents the links to your children, okay? Now, this isn't the whole story, because A, this will link to the children that are actually along the A branch, and so we get to this leaf in this case. Well, not yet, but almost, okay. Now we get to the leaf. And so the other side of the tree looks like this, and now we're done. So this is a simpler way of viewing the world, and while it seems initially very complicated, the thing to realize is this is literally just the same thing as that array of links where we used A, like index A, we stored a pointer, and index C and stored a pointer. Here we're having a tree of those objects. And the internal structure here, what does that mean? It has no meaning in terms of this original data structure, right? This is just by happenstance that it looks like this. Hope that made sense. So rather than storing as an array, you could store your links as a binary search tree. This is just some kind of map, all right? So this was a question that you already answered, so I'm not going to ask it. But more generally, rather than using some kind of tree, we could just use any kind of map from character to node. Okay, and that map tells us, given a letter, who's the appropriate node. And that means I showed you an example using a tree map, but you could also do it with a hash map or anything else. So what's nice about data structures, as I mentioned, you have these layers of abstraction, and then at any level you can kind of take pieces and use them. So in this case, it seems a little interesting that we can build some type of map that uses a map as one of its implementation details, but that's how it goes. And it's a real data structure if you use a tree map or a hash map. All right, any questions about this? Yeah. Yeah, so what does it mean to use a try map inside of a try map? I started thinking about that as I was talking. I don't know that it's well defined, but it's an interesting question because merge sort and quick sort are that, right? They are do some operation and then quick sort and merge sort. Here I feel like you're begging the question a little though, if you use a try map. You could break the character up into bits, and in that case you're basically just doing your basic, like somewhere some work needs to get done. So in merge sort, it's the merging operation. Quick sort is partitioning. If we just did try map here, there's no work getting done. But it's interesting to speculate. Is there some kind of recursive map thing? And actually, we have this same question that comes up. You think about hash tables. With a hash table, each bucket was ultimately some kind of set, and you could use a hash table in theory as well, and that doesn't seem to be very sensible. So what these, like, there's some point where the recursion, you're like missing a base case. So yeah. But it's a good question. Is there some meaningful thing where you have a try map whose maps inside of it are also try maps? I don't know. Other questions? All right. So each choice a map. Ultimately, it comes with its own runtime space trade-off. What the Princeton implementation in the textbook, optional textbook does, it's a data indexed array. It's very fast, but it uses tons and tons of memory. A tree map or a hash map, it'll be a little slower because you have to traverse this tree, if it's a tree map, to find the links, but you save lots and lots of memory. And you can mitigate some of those performance issues by making sure that your hash map that you create, if you're using a hash map, starts off really small. And there's a bunch you could do with this. Okay? There's a whole world of possible data structures. And if you ever go into the world of writing like back-end servery stuff, or if you get into databases, that's where you're going to try and squeeze all this performance. And anybody want to guess, how do you decide whether a tree map or a hash map is better in this circumstance or not a try at all? What do you think? Yeah. Well, I think the real answer is not that you think about it. It's that you just implement them all, you profile them on real data, and you pick the one that seems to work best. And that's fine. That's very common. I mean, I think that was a big insight. When you take 61C, you'll learn about architectures, and there's a lot of decisions in hardware that are not beautiful in the same way that hash tables are beautiful. And you'll learn about like caching. Like caching is a cute idea in hardware, but it's not beautiful, and there's all these little decisions. You wonder, well, like, how did they decide to have 16 kilobytes of this and 64 kilobytes of this or whatever else? And the answer is just, well, they picked some arbitrary answers, they did some profiling, ran some simulations, and that one seemed to work best for real-world loads. So be aware, that's a common thing. Now, it's not something most computer scientists do, which is that tuning the last 5% out. But if you like it, like if you're somebody that when the autograder says you have failed the 3x test, and you're like, great, let's spend like, a day like really getting my number so that it says I did 0.00x this staff solution, then maybe that's the thing for you. Systems building. All right. So my last 5 minutes, I'm going to talk about sort of a quirky variant of a try. This is something that is taught, as far as I know, nowhere in Intro CS other than Princeton and here, and just because I happened to be at Princeton before, I brought it with me. But it's a cute way where instead of having tries that have an arbitrary number of links, we have tries where each node has only 3 links. And those links represent characters that are less, equal, or greater than. And it's a little bit of a hybrid in some ways between something we might think of as a binary search tree and a try. So let's see it in action just to see what's going on here. Okay? So in this case, I think it's better to... Okay. So this is my original... This is a normal try. It can have many children. Now in a ternary search try, it just so happens that there is no special root. Okay? So instead of having a root with nothing in it, here, there's a root, and in this, if you look at the implementation in the Princeton textbook, they do actually store letters inside nodes. So the student who asked earlier, could we store letters in nodes? Yes, and this approach does so. Okay. So after you insert Sam, this is the try you end up with. Now here's where it's going to get a little weird. Okay. So it looks pretty similar, there's no root. But now when we insert sad, rather than dangle the D right off of A, we are going to, rather than dangle the D off of A, that doesn't make sense. Because the semantics of a ternary search try is that when you go down, that's the way you indicate that you have matched. So, is S in the tree? Yes. Is A in the tree? Yes. But here I see the letter D is not there. So what I'm going to do is say, well, I'm going to store the D a little bit to the left of the M. So it's not as clean conceptually as the try, but it will have the property that every node always has exactly 3 links, so it'll save space. But it's harder to read these tries. All right, next one that comes up is SAP. Same deal. So if I want to insert SAP, well, I go S, A, M. Oh, but M's already taken, so I'm going to put P here. All right, next comes same. Well, with same, there is actually room below, like same is a suffix of Sam, so it's okay to go straight down below Sam. What about A? Well, A, what we do is we say, well, there's nowhere to go from, there's no root. We start with S. Now, A does not match S, so we go to the left. And so what's kind of funny about this is you have to go through S, which has nothing to do with the letter A, in order to store A, and then we end up with alls. Here's a longer demo. We have to download. Okay, I already downloaded it. Waiting for them. Okay, here we go. All right, we'll do another one. This time we're going to drag. Nope, that's the wrong direction. All right. It's a .movie file. So I haven't built my own, because it's sort of weird. It's not worth. Okay, so here's putting in she. In this case, they're doing a map rather than a set. Whenever you do cells, okay, we get to H, then we go down from, or go left from H, and it's covered up. All right, move thing. It's worth it. Okay, I'm going to talk through the next one. Okay, so next is going to be the word shells. So maybe try and anticipate what's going to happen here. So we try and put in the word shells. Okay, so it matches S, it matches H, it matches E, and then you go digging down. So if you're like someone who enjoyed Minecraft or something, you've found an area that had not been dug in yet. Okay, good. All right, how about the? So what's the going to do? So the root is S. Is S equal to T? No. So where do we go? Got to think about it. R, S, T. Okay, we'll go to the right. And then once we get to T, we basically staked out unspoiled territory. So where do we go from here? Down. Great. Dig straight down. Always safe. Okay, good. My Minecraft nerds are chuckling. All right. It's a really fun game, actually. That one and Kerbal Space Program are really good. Recommended. All right. Okay. You have to clap for yes. Say again? Oh, slide? Yeah. S-A-N? San? Yeah, so if we had san, then we would go S-A, M's already taken. Okay, so we need to go to the left. And then we get to D. What do we do now? We'd go to the right. And so san would get stored here. Unless I didn't say that right. L-M-N. Oh, N. N's better than a P. Okay, sorry. I forget my alphabet. L-M-N. Okay. And we go to the right of M and then the left of P. Yeah. So what that looks like, and I'm not going to go through an implementation at all, but you end up with a link, 3 links from each node. Okay. So my last thing I want you to think about is, now that I think you have a rough handle on this data structure, what's something you can insert into a ternary search try where the structure is worse than a standard try? Something that feels ugly. We got to go. All right. So, for example, inserting A, B, C, D, you end up with a spindly tree. So ternary search trees, tries, whatever you want to call them, are dangerous in that sense. But there's a whole, we could do another 3 weeks on balancing TSTs. If you're curious, there's papers out there about it. And so that's it. So summarizing, tries are really good for prefix operations. And really the important thing here is getting a taste of what other strange data structures are out there. But I'll leave those open to your future. All right. So next week we're going to see 2 utilizations of things we've done throughout class, and then we'll say goodbye. All righty. I'll be up front if you have any questions. Visitors, feel free to come up and ask questions as well.